Okay, so today I would like to present to you the project that my colleague and I have been working on for almost 2 years. And I would like to say that the COVID pandemic has posed an unprecedented challenge for healthcare system worldwide. One of the most serious complications associated with this disease is acute respiratory failure. This diagnostic and monitoring of acute respiratory failure in patients with COVID-19 has been one of the greatest challenges during the pandemic. The variability in clinical presentation, sorry, limitations in traditional diagnostic tools, lack of scientific specific biomarkers, uh, and overlap in intensive care units have complicated patient care. And the Flanders project was proposed to provide healthcare professionals with a tool to support early and high quality precision decision making in the treatment and management of COVID-19 patients at risk of acute respiratory failure through the development of an ontology-based clinical decision support system. For the development of the clinical decision support system, 6 clinical practice guidelines selected by the clinical research team were used as sources of knowledge. There are the 6 clinical practice guideline uses. The reference show that some are used worldwide like this. There are the other nationality. And this is the used in Spain, and still others are specific to the hospital where the tool will be piloted in this case. And this is the Flanders workflow. First, we selected the 6 knowledge sources discussed in the previous slide and choose the design for the ontology. In this case, we opted for the ontological step-based methodology, which ensures methodological rigor and facilitates traceability through the modeling life cycle. Second, we performed a structured extraction process to transform the unstructured clinical content into a tabular format suitable for ontological modeling. The resulting document was organized into 3 semantic sheets to facilitate semantic annotation and rule organization. Sheet 1, general concept. Sheet 2, ventilatory recommendations. And sheet 3, pharmacological recommendations. Ventilatory recommendations were labeled with the prefix V, followed by a numerical index, while pharmacological recommendations used the prefix T. And now, in this phase, we begin creating our ontology, which was defined in our steps and in 4 steps and designed using the Protege software tool. In step 1, we defined the classes, subclasses, instances, and properties. In step 2, we added class called recommendations and 2 subclasses called ventilations and pharmacological treatment. We then added the recommendations with their levels V or T. Sorry. Here we have the step 2. In step three, the relationships were defined by establishing properties and the rules were constructed. In step 4, the clinical terminology was standardized using SNOMED-CP to ensure semantic interoperability. And after creating ontology, it had to be connected to the CDSS. And to connect this, logic engine implemented with the, to connect the ontology with the CDSS logic engine implemented in Python, a semantic translation process was developed. This process automatically extracts the logical rules associated with each class from the all actions and transforms them into a structured representation. These translated expressions can be directly evaluated using a set of clinical variables that are initialized with patient data at runtime. And finally, our next step will be to pilot the Flanders tool primarily in a real-world setting. The main contribution of these works lies in the design of an ontology capable of representing clinical knowledge in a computable and interoperable format, while maintaining semantic accuracy and alignment with international standards such as SNOMED-CP. The seamless integration with the CDSS demonstrates the feasibility of ontology-driven decision support in real-world clinical practice, where complex decision rules such as those related to ventilatory strategies or pharmacological interventions can be executed dynamically based on patient-specific context. Overall, these findings support the use of ontological frameworks as a robust foundation for next-generation clinical decision support systems in acute care scenarios. The ontology construction process led to the development of a formal knowledge model using Protégé, which incorporates more than 90 clinical recommendations related to ventilatory support and pharmacological treatment of patients with COVID-19 and acute respiratory failure. The ontology also defines mechanisms for prioritizing and mutually exclusive recommendations, helping to resolve potential conflicts and ensure clinical consistency. In this work, the CDSS was implemented using a standalone Python-based engine, rather than adopting standards such as CDS hooks. This approach provided maximum flexibility for defining and evaluating complex clinical logic without the limitation imposed by predefined data models or integration protocols. It also allowed the systems to be developed and tested independently of any specific electronic health record system, making it particularly suitable for academic research, offline validation, or deployment in environments where CDS hooks are not yet supported. The Andalusian EHR, Diraya, is an example of this, with a technological environment that is often outdated and does not allow for true interoperability with this type of tool. One of the key challenges of this approach lies in its reliance on explicit logical rules defined over binary clinical variables, which must be manually initialized for the system to function properly. As more recommendations are incorporated into the system to function properly, as more recommendations are incorporated into the ontology, the number of required input variables increases, raising the complexity of preparing patient data for each case. The system also depends heavily on data completeness, as the absence of a single relevant variable may prevent important recommendations from being triggered. These limitations will be mitigated by obtaining patients' background information, reading it through a language model, and automatically extracting the variables. Furthermore, the project has not yet reached the pilot phase, so it has not been possible to carry out functional validation of the ontology or verification of the behavior of the inherence engine and decision rules. Following the functional validation phase, the ontology will be published on Bioportal. Thank you very much.